Hi guys, this is Mrs. Gastler, and in this video we're going to talk about work and power. And so let's get started. So work, you've probably heard about work, but this is going to be physics work, which is going to be a little bit different. So some of the things that you think are work are not going to qualify as work here, because in physics, work is done by a force on an object if it causes the object to change position. Sometimes we're going to use work to mean something a little bit different, but in the mechanics part of physics, this is really all we can use it to mean. Later on, we start talking about energies. We'll define it just a little bit differently because we can, and it's okay. We'll come back to that again later. So I've drawn you a diagram here. We've got some sort of object right there, that little box, and there's a force on it, and that force is moving that object through some change in position right there. Sometimes if we're dealing with one dimension, we can use the word distance interchangeably with change in position, and sometimes we can't. So it just kind of depends. But notice that if there's no force, there is no work. Okay, so if you're not applying a force, you are not doing work according to physics. And if there is no change in position, you are not doing work according to physics. But we are also going to add a little bit more here in just a couple of these colors that I'm going to take off. That's going to make it even more interesting. Okay, so how do you find work? Well, the equation looks like this. It's W for work equals F, and then there's a little dot there. That little triangle poking out is underneath the yellow. F dot D. Dot is an operator in physics. Whoops. This would make more sense if I included my little, what color am I using this one? Got the size here. The little indicators that tell us that force is a vector, and so is that position. That change in position is also a vector, okay? And so what we're doing is we're doing math with vectors, which in AP Physics 1 you really can't do yet. You don't have the math skills. You're only in Algebra 2. If you're taking Calculus 3, then you might know something about vectors. If you're in one of the lower calculuses, you may be somewhat familiar with some of these vector operations, but that's okay. You don't have to know how to do this right now. We're gonna kind of baby step around it. We're gonna teach you that to do a vector product. Well, this is actually a scalar product of vectors, but we're doing a product of vectors called a dot product. Okay, it's literally pronounced dot. Dot product, and there's a dot in between them. It doesn't mean times, but it kind of does. When you multiply vectors, there's two ways you can do it. You can multiply vectors and come out with a number, and you can multiply vectors and come out with another vector. And this one, we're coming out with a number. And so work is not a vector, it's a scalar, which is just a number. It doesn't have magnitude. And so when you do that, you do work equals force times distance times the cosine of the angle between them. So if my objects, I'll draw another little picture here, if my force is directed this way, but my object is traveling this direction, then there's some angle between them, and that is the angle, this is distance, that is the angle that I would put in there. And you want to make sure that your calculator is in the right mode, degree or radian, depending on what you're given for that angle, okay? And so that's what we would be putting in there. So what does this tell us about that angle? Well, it's telling me that my timer's going off. Well, if the cosine of 0 degrees is 1, so if they're in the same direction, then work equals force times distance. If we were in baby physics, that's what we would be doing, force times distance, okay? If a cosine of 180 is negative 1, so if they're in opposite directions, then work equals negative force times distance. That just means that the work there is actually taking away from what the object is doing, which we'll understand that a little bit more when we talk about the energy aspect of what work is doing. So that'll make sense in maybe the next lesson, we'll see. And then cosine of 90 is 0. So when they're perpendicular, that means that no work is actually being done. So by that force on that object. Work might still be being done, but it's not by that force on that object, okay? So that's a distinction we need to make. Work can still be being done in a situation, just not by that force on that object, okay? So let's talk about some units. Units are going to be interesting. So for force, force is measured in newtons. 1 newton is at 1 kilogram times 1 meter per second squared. Distance is in meters. So when we find the units for work, which is force times distance, we're just going to be multiplying all of that together. So a newton times a meter, which is a kilogram times, now there's 2 meters in there, so there's meters squared times divided by second squared. That is called a joule. This guy named James Joule, he got to name that unit after himself, spelled Joule, abbreviated J, okay? Oops, I gotta scroll here. All right, so let's talk about what we can do with that graphically. Graphically is something that we often do in physics. So we're going to graph a distance of force versus distance, and we're going to look at constant force first. Most of the time we're going to be dealing with constant force because we lack the calculus skills to do anything else. So constant force is what we're going to look like, and a graph of that is going to look like this. Nice, beautiful straight line because the force isn't changing, okay? Force measured in newtons, distance measured in meters. So since the work equals force times distance, hopefully you can see that that's found by finding, yeah, that sounds weird, the area under the line. So that would look like this. So there we've got a box that we've drawn. So over this distance, how much work was done? Well, we just find the area under that line. Force times distance would find the area of that, right? Length times width. That's really what we're doing. So we can take that and we can apply that to, well, what if the force is not constant? Well, what if our graph looks like this? Oh, there's a piece of the graph missing there. You'll see why in a second. So our force increased and then it was the same, okay? So maybe you were driving a car and you pushed a little harder on your gas pedal over and over and over again until you got on the highway and then you kept it nice and steady as you were traveling down the highway. Well, so the force was changing at the beginning, okay? So we have to take into account that it wasn't a constant force the whole time. Well, we can do that graphically, even though we can't really do that mathematically using formulas yet because we don't have the skills to cope with that right now. But we can look at it graphically and still do the same thing. So work is force times distance. It tells it graphically it's the area under the curve. So we can still do that, right? You can find the area of a triangle, right? So we can do that. We can find all the shapes. If it looked all kinds of wonky, we could just add them all together. So that's what we would do. So we have the work for that part of the first triangle, and then we've got another square right there. We would just find those areas and add them together, okay? So that it's the area under the curve that tells you how much work is done. No matter what the shape looks like, it's still that area, okay? Now, if it's weird and wonky and curvy, you might not be able to calculate it, but you could still tell, like estimate, well, it looks like it's bigger under here than it is over there, so more work was probably done here, okay? And that is probably as much as AP Physics 1 might ask you to do with curves. Not straight lines, that is, okay? So let's talk about power. Power is the rate that you do work. So work and power and energy are things that people confuse a lot. So they think that those words are kind of interchangeable. Like energy and power are actually very often confused because, you know, we go to the power company, but they're not really selling us power, they're selling us energy. But we use it to power a house, which is not really the right word either. Yeah, it's kind of confusing. So in physics class, power is how fast you can do work. Okay, it's how fast you can use the energy. It's how fast. It's a how fast, and it has to do with energy because it's a rate. It's a rate that work is done. So that equation looks like this: work divided by time. Okay, a rate is always something divided by time. So here, power is work divided by time. P for power. That's easy, right? The confusing part is going to be when we get to the units, which I think is maybe next. There it is. Okay. So work is joules, T is time. There it is, joules per second. In ugly units, oh, that's later. Okay, so a joule per second is named after this guy named Watt, James Watt. So these are watts, and that's a W, okay, and that's where it gets really ugly, right? So we have work for W for work, and we have W for watts, and the difference is that the W for work, I can make a note here. The W for work is always going to be in equations. And the W for watt will always be after numbers. Okay, and you won't see them mixed up like that. If you see a W in an equation, it doesn't mean watts. Okay, and if you see a number and it's followed by a W, it doesn't mean work. There's no 60 work. It's not a 60 watt light bulb. Okay, it's a 60 watt light bulb. Okay, and you're not going to put in 60 watts up for the work. That's not what's happening. Okay, so if you can keep those things straight, then you'll be okay. And then when we do like we did up here with the right there, if we do what we did right there with the Newton meters, we can do that with this one too. We end up with joules per second is a Newton meter per second, which is a kilogram meter squared per seconds cubed, and those get even better as we just keep going. I love them. Okay. All right, so last thing here. Sometimes power is written in terms of force because work is force times distance. And so if we plug those in and we have a little bit of fun, do you see it right there? The distance divided by time? That's just speed. And why is there a random circle there? Okay. So force times the speed. So if you have an object that's moving at a constant speed, or you can find an average speed for it, like in our car that we were driving on the highway, the force times the speed would give us the power. Oh, you know what? I forgot something also. There's another thing that we can graph. If we graph work and time, the slope of this line is something meaningful. Look at me writing very pretty, not too zoomed in. Yeah. The slope of this line is going to be power. Okay. P, let's see, because it's y equals kx, and so y is w and k times t. So that follows the same format of this equation over here. Work equals pt. And so the power is going to be work, and the other way, work times time. So the rate at which work is done is power. And so the slope of that one is power. Okay? And so that's all I have to tell you about work and power right now. We're going to do some activities about work and power, hopefully today or next time. And that's about all I have to say. Thanks for watching.